All right, good morning, everyone. Can you guys hear me? Okay, all right, fantastic. So let's jump right into it. We're going to start a new chapter today, and the title of this chapter is going to be pericyclic reactions. And in your textbook, that is going to be chapter 24. So chapter 24, pericyclic reactions. And this is one of the class of reactions that we talked about that occurs next to the polar reactions and the radical reactions that we will cover later in this semester. Now, I want to start with a general introduction into pericyclic reactions and what are the characteristics of these reactions. How do they distinguish themselves from the polar reactions that we've been talking about previously. And then I'm going to go, most of today's lecture is going to be like an overview of the different types and how we classify them. And if we have some time, we're going to start going into the first subgroup of these reaction types. Okay, so what are the characteristics of pericyclic reactions? And they follow some very general rules. So what is key to pericyclic reactions is that they have a cyclic transition state. And that's kind of built in the name already, right? So have a cyclic transition state. And what that means, we'll come into that a little bit later in much more detail. Now, the next big point is that we classify these reactions as concerted. That means that the electrons that are involved in this reaction break bonds and form bonds essentially simultaneously. So it's not a stepwise process, but it's a process where bonds are formed and broken more or less at the same rate. Reactions are concerted. And that basically, this word concerted means that electrons break and form bonds at the same rate. So electrons break and form bonds at same rate. And that's essentially the definition of a concerted reaction. And what is part of this, essentially, the fact that bonds are broken and formed at the same rate, is that there are no real intermediates to these pericyclic reactions. They usually have one transition state that they go through, but there is no cationic or anionic intermediate that then goes through another transition state into the products, right? So there are no intermediates. And the last thing that is relevant to pericyclic reactions is that many of those reactions are potentially reversible. So anytime we look at those, we have to pay attention to whether we are performing the reaction in the forward sense or in the reverse sense. So both are oftentimes possible. All reactions are potentially reversible. And we'll talk about this a little bit more once we actually get into the specifics. But what I want to start today is kind of introduce the four categories, essentially, of pericyclic reactions. And you can think about these as subcategories of the bigger picture of pericyclic reactions. And we just want to categorize them into four groups. So the first one here are cycloaddition reactions. And sometimes we group into this, in this subcategory, also a subclass, which is the cheletropic reaction. And I will introduce all of these so that it makes sense in just a second. So the second most common class of pericyclic reactions are electrocyclizations. Electrocyclizations. And these are reactions that are related to the cycloaddition reactions, but they are distinguished by the fact that they are usually monomolecular. So they occur within the molecule itself without having like two partners or two reagents. The third class is sigmatropic rearrangements. So this is a class where essentially a sigma bond moves along a pi system, and we'll give some examples for that in just a second. And the last class, that's kind of a smaller class, and we have seen these already, we just haven't identified them so far as pericyclic reactions. These are the group transfer reactions. All right, so this is basically the very, very broad overview of what we are going to cover over more or less the next 5 lectures. They are all pericyclic reactions, and we put them into subcategories that are the cycloaddition reactions / cheletropic reactions, the electrocyclizations, the sigmatropic rearrangements, and the group transfer reactions. They all share these fundamental properties that we have written up here that distinguish them from the polar reactions that we have seen before. So they have a cyclic transition state. They are concerted, means that the bonds are broken and formed at more or less the same rate. There are no intermediates. There's only one transition state that basically connects starting material and products. And all these reactions are reversible. So whether you go from the starting material up to the product or the other way around, that's basically the same mechanism, the same transition state, essentially the same pericyclic reaction. All right, so after this very broad overview, we want to start going into the subcategories here. So the cycloaddition reactions, the electrocyclizations, the sigmatropic rearrangements, and the group transfer reactions. We're just going to talk about those today in the context of what makes them distinguishable, or what are the unique characteristics to these reactions. And starting next class, we're going to then jump deep into the mechanistic details of each of these categories, right? So let's start out with the cycloaddition reactions, because that's kind of like the most common category that you'll see. So cycloaddition reactions. And we can call this subgroup 1, essentially. Now, the critical feature of cycloaddition reactions is that you have 2 independent pi systems that come together to form new sigma bonds. So 2 independent pi systems come together to form sigma bonds at the ends of these pi system. And as part of this process, usually you form a ring. So that's why you have this term cycloaddition. And they can both be intermolecular as well as intramolecular. But let's look at a simple example of a cycloaddition reaction that you'll find in your book. And that is kind of like the classical Diels-Alder reaction. Now, what you're dealing with in a Diels-Alder reaction, let's look at the very simplistic, very generic model here, is that you have two independent pi system. And in a Diels-Alder reaction, these are usually a diene and a dienophile. And in this case, the simplest combination of diene and dienophile that you can think about is butadiene here and a simple olefin. So we call these the diene, and this is the dienophile. And what these do as part of the Diels-Alder reaction is that they extend their pi system from one partner to the other to form new sigma bonds. And the easiest way to denote this is if you just follow this 2-electron pushing rule. So you push 2 electrons from the pi bond over here. These 2 electrons in the pi bond move over here, and the electrons that you had over there move in to form a new sigma bond between these two ends of these two pi systems. So what you get out of this then is basically a cyclic structure, a 6-membered ring in this case. These 2 electrons formed this new sigma bond, so that's this bond here. These electrons that come from here formed a new sigma bond between these two nuclei. So between this one and this one, this one and this one, these are the 2 sigma bonds that we're forming. And if we push these electrons around, they basically form a double bond in the back of the system. So we essentially then end up with 4 electrons in the sigma bonds, and you have 2 electrons in the pi bond here. And if we look at our starting material, we actually can find these electrons again. Remember, those were the electrons that formed these 2 sigma bonds, and we have these electrons that formed the pi bond. So we're talking about the same electrons that were occupying the pi system previously. And in this system here, we had 4 pi electrons, so we usually call this 4 pi. And in this system, we had 2 pi electrons, so 2 pi electrons that basically formed, in this case here now, 2 pi electrons plus 4 sigma electrons, right? So that's basically the sum of electrons, just to kind of keep count of what's going on. Now, usually these reactions work under thermal conditions. So the classical Diels-Alder reactions work under thermal conditions. So in order to push this reaction, you essentially have to heat up the two components. Now, there is a way to kind of classify these reactions based on how many electrons are involved in the system. And we just want to go a little bit over the nomenclature of these cycloaddition reactions, and they're usually classified by a bracket that contains 2 numbers. Let's say m plus n. And m and n correspond essentially to the numbers of electrons that are in the corresponding pi systems that react with each other. So this is, for example, in this case, m equals 4 electrons and n equals 2 electrons. So in this case, then basically we are dealing here with a 4 plus 2 cycloaddition. So we're just basically counting the electrons in the pi system. This is 4 pi electrons, this is 2 pi electrons, and we basically combine them as these integers in this square bracket. So a Diels-Alder reaction is always going to be a 4 plus 2 cycloaddition. Now, of course, these reactions, as we said previously, are not just reactions that work in the forward direction, but they can also work backwards. So we can call this the retro Diels-Alder. So the same way that we formed a 6-membered ring with a double bond, we can basically break up a 6-membered ring with a double bond. So if you think about it this way, you can also perform the reaction under the appropriate conditions in the opposite direction. And this is still going to be called a cycloaddition reaction, just that now we are looking at this essentially in the reverse reaction. So we again have our 4 pi electrons, and we have our 2 pi electrons over here. So overall, the class of Diels-Alder reactions are in total 6 electron processes. We always have 4 electrons from the diene, and we have 2 electrons that pair up with it from the dienophile. So the total electron count in these systems is 6 pi electrons. Now, these reactions do not always have to have 2 independent pi systems, molecular pi systems that come together in the reaction. But of course, you can imagine systems where this reaction proceeds in an intramolecular process. So intramolecular Diels-Alder. And just a simple example, you could think about it this way. If we have a diene and this is linked through a saturated linker, for example, to a dienophile, you basically still have exactly the same components. So you have your 4 pi electrons on this side, and you have your 2 pi electrons on the opposite side. Now, it happens to be that this is linked now into a continuous chain, but the process is exactly the same. So you can take these electrons, push them over here, take these electrons and push them over here, and take these out and push them here. And then in a concerted reaction, you essentially form 2 new sigma bonds between these 2 ends here. And if you heated this up, you end up with an annulated, 2 annulated 6-membered rings and a double bond on this side. So these were basically the previous position of the ends of the pi system. So these were these carbon atoms here that came together to form these 2 new sigma bonds, right? So in this case, you have now 2 pi electrons, and you have 4 sigma electrons in this system. So again, this all qualifies still as a 4 + 2 cycloaddition. So it falls in the category 4 + 2 cycloaddition. Okay, but if we really look deeper into this, into these cycloaddition reactions, we are not tied down to this schematic that we see here as the classical Diels-Alder system, where you have a diene and a dienophile that react with each other, and where you're locked in basically into this total of 6 electrons. But there's higher order reactions where you have essentially other combinations and different electron counts that still fall under this greater category of cycloaddition reactions. And just so that you get used to that, I'm going to show you a couple of examples that you will see throughout this series of lectures. And one of them, for example, let's pick something like, let's do 10 + 2 cycloaddition, right? So now I still have an olefin here with 2 electrons, but now the other pi system contains significantly more than the 4 electrons that I was talking about previously. And if you think about this, you could build a pi system, for example, that looks like this. And then a diene on the other side. And now all you need to do to figure out whether this is going to, how the electrons are moving through the system, you basically just have to count the electrons in the individual components. So in this case, we clearly have a 2 pi system here. So that's basically this part of our nomenclature, right? So in the olefin here. And in this system, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So this is our 10 pi electron system, right? Now, if you're asked now to draw the arrows out to push the electrons around the system, you can start, for example, at this end of the pi system, push it over to this double bond. The electrons in this double bond, you can push them over to this end. And then as you proceed around the system, it becomes very quickly clear that you move all 10 electrons in a concerted way, in a synchronous way, essentially around this entire pi system. And if you performed this reaction, thermally, your product would then be an annulated system again. So in this case, you can form an annulated 6-membered ring here. So let's draw this out. So these were the carbon atoms at the ends of the pi system that reacted with each other. These are the new sigma bonds that we're forming. And now we just have to make sure that we place all the double bonds in the correct place. So this one ends up here, this one ends up here, and it's symmetric on the bottom side. So the only distinction now is that we had in one component significantly more electrons, but in principle, the mechanism of the reaction works exactly the same way. You push the electrons around in a circular manner. And these are kind of like the two new sigma bonds that you're forming as part of the process. So this was kind of like a 10+2 cycloaddition. We can look at another example. Let's say something, let's do 8+2 cycloaddition. And I'm sure by now you kind of start seeing a pattern emerging here. So it's always kind of like a pi system that in one case, in this case, for example, has 2 electrons. On the other side, it has now 8 electrons instead of the case up here. And you basically just can put together something. Let's see, let's do something a little bit more complicated. So this is our 2 pi system here now. So these are kind of like the olefins, or this is the olefin that we're talking about. So it's the 2 pi electron component. And then we can build like a heterocycle down here that could act as a partner. Let's put a nitrogen atom here, and then 1, 2, 3, 4. Okay, so in this case now, if you count the electrons here that you're reacting, so you would react this end of the pi system and this end of the pi system with the corresponding ends on this side, then you would have an 8 pi electron component down here in the system. So this would be 8 pi electrons. And you can go through this exactly the same way as we have done before. So you can take these electrons and push them out here, move these around. These ones move over here. These ones move over to this side. And this electron pair here moves out to form the new sigma bond between these two carbon atoms. And again, you basically formed an annulated species in this process of the reaction. So let's draw this out. Nitrogen here. And then we had 5-membered ring. And now we just have to make sure that we actually moved the double bonds correctly. So this double bond here shifted over to form a double bond here. This one shifted over to form a double bond here. And this one shifted over to form a double bond here. So this would be, for example, a simple example of an 8+2 cycloaddition. Now, so far we only ever had like as a partner this 2 pi electron system, but these cycloadditions are not limited to that. So you can really go crazy with this combination of electrons. And I just want to show one last one, and this is a 6+4 cycloaddition. And in this case, we have, again, an intermolecular species. So we have a component that has 4 pi electrons. So these are basically the ends of the pi system that will be reacting. So this is 4 pi electrons. And then as the partner component, we have something that has 6 pi electrons. And this is essentially a 7-membered ring with 3 double bonds. And these are basically the 2 positions that will be reacting with each other. So this is our 6 pi electron system. Now, if you let these 2 react with each other, they come together and form a new bond essentially between these 2 positions and these 2 positions. And if I do that, I can start pushing the electrons around if you want to. So we can take these electrons and move them over here. Take these, move over here. These move over here. These move out to form this bond here. And these move over into the back there. And that actually gives us quite a complex structure already. So it's a tricyclic system in this case, where, let me see if I can draw this out properly, where you have, this is basically this fragment over here. We end up with 1 double bond here, and then we have to extend our system like this. This goes up again. Let's do it like this. And then there's 2 double bonds over here, and you're still left with this 7-membered ring. So if you count through the atoms here, these were the 4 atoms that we formed new sigma bonds between. This is the 5-membered ring, and this back here is essentially your 7-membered ring, right? So this would be an example of a classical 6+4 cycloaddition. And even in these systems, if you were to come in and count the total number of electrons that are in the product, it actually matches perfectly what we see here in the 6+4. So here you have 4 electrons, here you have 6 electrons. If you were to count them here in the product, you have here 2 pi electrons. You have from each of these, you have a total of 4 sigma electrons. And then back here, you have another 4 pi electrons. So total count here is 4, plus 2 is 8. So 4 plus 4 is 8, plus 2 is the total of 10 electrons. So you're not losing electrons in this case, and that's a good sanity check whenever you draw these reactions out to make sure that, that you have accounted for all the electrons in the system. All right, so these were just a couple of examples of cycloaddition reactions. We're going to go much more into detail with these and talk specifically about how these reactions work, but I think it's a good way to introduce them, just to give you an idea of what complexity of reactions are accessible through this and what combinations are out there. Now I want to shift a little bit over, still in the theme of cycloaddition reactions, but we want to look at the other subcategory that I mentioned earlier, which were the cheletropic reactions. So cheletropic reactions. And these are basically just a subcategory of the cycloaddition reactions. And the unique part about cheletropic reactions is that they form 2 sigma bonds to the same atom. Form 2 sigma bonds to the same atom. So previously with the cycloadditions, reactions, we attached or we formed new sigma bonds at the ends of 2 pi systems. Now we do this a little bit differently. We actually form the 2 sigma bonds to the same atom. And the simplest case is for example, the reaction of an olefin, so it's a 2 pi component, to a carbene. So if we have, for example, something like this, this is a carbon atom here, and you have residue R, and the carbene basically has two two lonely valences there. Of course, this is not something that is often considered a stable species. Most of the time, these are generated in situ as highly reactive two electron components. So this is a carbene, and it has two electrons. The chelotropic reactions work exactly the same way, where you can take the electrons basically from this side and push them over to this pi system. And this pi system, the electrons in this pi system, you can take them out and push them back to this carbon atom. And what ultimately this leads to is essentially the formation of a three-membered ring. So it's essentially the carbene addition across a double bond. So you have a three-membered ring here now with your carbon atom, and then you have residues R and R. So formally, if you were to count this within the nomenclature that we would develop for the cycloaddition reactions, this would clearly fall under the category of a 2+2 cycloaddition reaction, right? So because you have two electrons here and you have two electrons over here, so the sum of M plus N is 2+2. Now, another reaction that falls within this umbrella of chelotropic reaction is the reaction of a 4-pi system. So 4-pi electrons. So if we have like butadiene, for example, and the reaction of butadiene with sulfur dioxide. So SO2 looks a little bit like this. It's an angled molecule where, again, there's a lone pair with two electrons at the sulfur. And this acts exactly the same way as we had the carbene react here. This reacts as a two electron component here. And we can now basically push the electrons again from here around the ring, from here back to the sulfur. And in this case, we're not forming a 3-membered ring, but in this case, we're essentially forming a 5-membered ring in this reaction. So this is then SO, and then we're ending up with a double bond here. And the ends of the pi system on the 4-pi component are essentially these ones here. And they connect to the same sulfur atom. So the two sigma bonds are formed to the same sulfur atom. And in this case, obviously, if we apply the same nomenclature, this would then fall under the category of a 4+2 cycloaddition. Right? So among all the cycloaddition reactions, the chelotropic reactions are a subcategory that just distinguishes itself by forming the two new sigma bonds to the same atom rather than to opposing ends of an extended pi system. So that's basically the only key distinction for these reactions. Okay, so after having talked about cycloaddition reactions, we want to move on a little bit and introduce the second big class of pericyclic reactions, and those are the electrocyclizations. And the characteristic feature why electrocyclizations are treated differently than cycloadditions is that they involve a conjugated pi system. So this would be our subgroup 2. And they involve a fully conjugated pi system. So it's not two isolated pi systems that react with each other, but it's a fully conjugated system. And just to give you an example, if you look, for example, at hexatriene, let's draw it in a ring structure or in a pseudo ring structure already, so that it's easier to see. So if we use, for example, this is a 6-pi electron system, and You don't need another component for this to undergo a cyclization. All you need is basically to arrange it so that basically the opposite ends of these pi systems come close to each other. So these need to be close. And then you can basically take your electrons and push them around this ring to form a new cyclic structure. So you can take this, and then what you get out of it is a closed six-membered ring where you formed only one new sigma bond, and you have two remaining double bonds in the system. So these were these carbon atoms over here where you formed the new bond. So this is sigma bond, so two electrons, and then you have two pi bonds that have four electrons. So the total electron count again comes up to the 6 electrons that we had originally in the system. And again, there is a somewhat different, a little bit different nomenclature for these systems. We usually call these out just by the total number of pi electrons that are involved in this system. In this case, we call this 6 pi electrocyclization. All right. Now, of course, there's different variations of this, and I'm just going to give you an example of another electrocyclization. And remember, these reactions can go either way, even though I drew the arrow here predominantly in this direction. The reverse reaction is significantly slower, but it's still possible. And depending on what kind of pi system you're specifically dealing with, it might be that the reverse reaction is actually favored. So this is the example that I'm giving you here. So if you have a strained 4-membered ring with one double bond in there, cyclobutene, for example, this preferably goes backward and forms the butadiene system that you have over here, right? So formally, you can think about this again as a four electron system. So in this case, it's obvious you have 4 pi electrons, but it's worthwhile thinking about where these 4 electrons are in your cyclobutene. So you have 2 electrons back here, so 2 pi electrons, and you have here, you have 2 sigma electrons, right? So the total number of electrons are again 4, the same way you have them on the other side of this arrow. And if you were to draw out the 2 electron mechanism, you could push these electrons over here, and you could take these electrons and push them essentially over here. So you're breaking the sigma bond and forming these 2 new pi bonds. Right? So you can think about this as a retro electrocyclization, but we group them all together essentially in the same category of electrocyclizations, no matter whether they go forward or backward. In this case, this is a 4 pi electrocyclization. Now, just to make this very clear what the difference between cycloadditions and electrocyclizations is, I just want to basically put this example right next to each other. So say difference between cycloaddition and electrocyclization. So let's look at 2 examples so that we have them right next to each other to see what the key differences are. And we're going to do an intramolecular mechanism here. So let's do something like this. And we have, let's say we have a double bond over here. And I'm just going to abbreviate this here. This is linked by some alkyl chain to the other end of the pi system. We already know that this is essentially the 4+2 cycloaddition, the same way we have seen it before. And we can push the electrons around in this system from here to here, this over here. We can push these in over here, and we end up with the classical formation of two new sigma bonds as we have seen this in the Diels-Alder reaction so far. So we have two different pi systems. So they're connected essentially here by an aliphatic residue. They are not conjugated to each other. And the product has usually one double bond. In the case of a 4+2 cycloaddition. Has one double bond and let's say two sigma bonds that are formed between these two ends, right? Now, how does this look like for an electrocyclization? So in electrocyclization, remember the key difference was that it was a conjugated system. So if we draw a similar structure to this, we could draw it somewhat like this maybe, and we can again put an aliphatic chain here. This is some form of cyclic system that we have here. But in this case, we already have one of these sigma bonds here in place, and this pi system is a 6-pi system that is fully conjugated, right? And in this case, again, we can push the arrows around. We can push the arrows around, and we are going to get a 6-membered ring with two new double bonds and one sigma bond here. So this is then a continuous conjugated pi system that reacts. Conjugated pi system. And what we are forming is essentially a diene as the product. Right? So these are key difference, just putting the cycloaddition reactions on this side right next to the electrocyclizations and on this side, so this would be a 6-pi electrocyclizations. That you see over here. Okay. All right, so I'll leave it at this with the electrocyclizations for now. Unfortunately, in your book, there is not a lot of material on electrocyclization, so we will dedicate an entire lecture to that, talking much more about how these reactions work and what the products are that you can expect from these reactions. All right, so that kind of closes the second subgroup of pericyclic reactions that we have been talking about. We want to move on to the third one, and those are the sigmatropic rearrangements. So this is the third class, sigmatropic rearrangements. And the key here is that you have essentially a sigma bond that moves around a conjugated pi system. So a sigma bond moves across a pi system. And the classical example of a sigmatropic rearrangement is essentially the Cope rearrangement. So that's kind of like the prototypical example of this class of reactions. So if you look at this closer, it's essentially a system that has two double bonds, and we can draw this out like this. And let's just basically give it two substituents. I'm just generically going to call them A and B here. This is basically just to keep track a little bit of what's going on. And as part of this reaction, what happens is that this sigma bond that connects basically this position and this position moves across the pi system and basically ends up over here. So if you were to draw out the electrons in order to make this work, you could basically take these electrons in the sigma bond, move them over here, take these electrons and move them out to form the new sigma bond between these ends of the pi system, and take these electrons out and move them over to this side. So the product, what you see, is essentially something that just scrambled the position of the sigma bond to the other end of the molecule, and what you're left with is now something that looks like this. It still has two double bonds, but the sigma bond changed position. And the way we usually do this, the nomenclature in these, is that we basically count the positions of atoms that the sigma bond moves across the pi system. And to make this a little bit easier, there's a trick that we usually do. We just number basically the carbon atoms from the sigma bond that moves to the other end of the pi system. So in this case, for example, we can say we can call this carbon atom 1, we can call this carbon atom 2, and we'll call this carbon atom 3. And on the other side of the sigma bond, we just call them 1 prime. We call this one here 2 prime, for example, and this one here is 3 prime, right? And that allows us to define that the sigma bond moves on one side of the system from 1 to 3. So this is basically the same thing here, 1, 2, 3, 1 prime, 2 prime, 3 prime. And on the other side, it moves from 1 prime essentially to 3 prime, right? So the new sigma bond is now between these two carbon atoms, 3 and 3 prime. And in order to kind of define this, we usually call this then a 3, 3 sigmatropic rearrangement, because it moves 3 atoms on one side and it moves 3 atoms on the other side. So we call this a 3, 3 sigmatropic rearrangement. And as you see, this is again a 6 pi electron process. It can be induced thermally, so 6 electron process. And the bond essentially that we're moving across the pi system, I can maybe highlight this a little bit here. This is this orange bond here that ends up on this side here. So this is the sigma bond. Moves along pi system. Now, maybe just to summarize this a little bit, what happens during these steps. So one, the sigma bond is broken and reformed in the same step. So this is still a concerted process. We only have one transition state here. So sigma bond is broken and formed in one step. We have already discussed the trick a little bit about labeling these atoms. That's very helpful to kind of keep track of them and how far the sigma bond moves. And then we have talked about like the numbering, also defining how we basically characterize these sigmatropic rearrangements. And just to give you an idea of the variety of sigmatropic rearrangements that you can encounter inorganic chemistry, I'm just going to go over two additional examples. So the first one is a 2, 3 sigmatropic rearrangement. So a 2, 3 sigmatropic rearrangement. So what we would expect is that the sigma bond on one side of the pi system moves by 2 positions, so from one atom over to the next, and on the other side it moves by 3 positions. Now I'm just going to show you the example where you can observe something like this. So let's do something like this, and then this is just 2 methyl groups. There's a positive charge here, and then you can have an oxygen here with a negative charge. So it's basically an N-oxide species that you have here. Now, if we go into our nomenclature again, we can say, okay, this is the sigma bond that is moving. So let's paint this orange again. So this is the sigma bond that is moving. And if we have a 2-3 rearrangement, we can count the atoms here. So this is 1. And this is 2, so the sigma bond moves from here to this oxygen atom. And on the other side, we have 1', 2', and 3'. So on the other side, it moves from this position over to this position. And again, essentially, we can draw out the product of this 2-3 sigmatropic rearrangement. And in this case, you probably expected this already. We have a double bond here. Then we go up, we have the oxygen here, and then we have a nitrogen, and we have the nitrogen attached to our 2 methyl groups over here on this side. Right? So the electron count in this system, you can go ahead and do the counting yourself if you want to, but you have 2 electrons here, so 2 pi electrons. You have 2 sigma electrons here, and then you have a lone pair here at the oxygen. So lone pair, 2 electrons over here. So this is still a 6 electron process in this reaction. So 6 electron process. And if you wanted to, you could essentially draw the arrows out for the arrow pushing. So you could take them from here down to this position, from here down to this position, and these electrons go to the nitrogen and form the lone pair on the nitrogen. So we could draw this in here just to keep the count correct. All right, and that basically then is another example of a 2-3 sigmatropic rearrangement. So we can draw the numbering here in again to make this clear: 1', 2', 3'. And this is the orange single bond here that we shifted across the pi system. All right, so let's look at one last one that falls in the class of sigmatropic rearrangements. And this is kind of like a little bit a special case, because in this scenario, you're not just shifting a sigma bond, but you're essentially shifting just one atom across the length of the pi system. And in this case, we call this 1-7 sigmatropic rearrangement. Sigmatropic rearrangement. And most often you see these as a hydride shift. So it's basically the movement of a hydrogen atom across a conjugated pi system. So classical example for that. Let's draw this out, and then let's make sure we can fit everything in here. Let's put the hydrogen here. And then let's put 2 substituent here so we can keep track of the ends of the pi system. And double bond here, and double bond over here. So if we do the numbering here, we can simply go by the same mechanism that we had previously. We have this is our sigma bond that we're going to shift here. So the carbon hydrogen bond here. In this case, there's nothing else attached to this. So in this case, we had like two atoms here, a nitrogen and oxygen. In this case, we only have a hydrogen. So our numbering is very simple on one of the components. So this is 1. And then on the other side of the sigma bond, we can have 1 prime, 1 prime. This is 2 prime, 3 prime, 4 prime, 5 prime, 6 prime, and 7 prime. And that kind of clarifies a little bit the nomenclature. 1, and on the other side of the pi system, you have 7 atoms. Now, if you heated this up, you would induce a shift. So this is then a total of an 8 electron process. And the product of this transfers this hydrogen here to the other side of the pi system. So if we draw this out, then you have something that looks like this. And then here you have your hydrogen. So the sigma bond that you shifted now is essentially this one here between the carbon and the hydrogen. And if you stick to your numbering here, you still have 1 over here. And this one was your 1 prime end, 2 prime, 3 prime, 4 prime, 5 prime, 6 prime, and then 7 prime. And you see that you shifted this hydrogen from the 1 prime end to the 7 prime end. And if you wanted to, again, you could think about like pushing electrons around here. So again, this is kind of a cyclic mode. You push them over here with the hydrogen, so that's why it's called a hydride shift. You can take these electrons, move them over here. These electrons, move them over here. And these electrons move in here to form this, this double bond over here. All right, so this is a classical example of a 1,7 hydride shift. 1,7 hydride shift. And it falls in the category of these sigmatropic rearrangements, the broader category of sigmatropic rearrangements. All right, so the last part of this lecture, we're just going to cover the fourth category of pericyclic reactions, which are the group transfer reactions. And this is our number 4. So group transfer reactions. And we actually have seen some of these before, and you will very quickly recognize them as a type of reaction that we have already discussed as part of the aldol chemistry that we are talking about. What is characteristic to group transfer reactions is that it's essentially a sigmatropic rearrangement that involves an addition or fragmentation. So it's a transfer of a group in a sigmatropic rearrangement that involves addition or fragmentation. So addition would be the forward way, and fragmentation would be the reverse reaction. So again, this is an example of a reaction that can go either way. So just to give you some quick examples, we're going to talk much more in detail about this at a later stage. But what you can expect from these reactions, a classical one is called the Ene reaction. And this is essentially a reaction that involves a hydrogen atom that is attached to an allylic system that reacts then with a double bond. So in this case, for example, we can have something like this. So this is the classical example of the addition, so the forward type of this reaction. So if we take the arrow pushing here, we take the electrons out of this bond and form a new bond here between the carbon atom and the hydrogen. We take these electrons and form a new bond between these ends of the pi system, and we take these electrons out and form a new bond over there. So what it essentially adds is an allylic residue to a double bond. And you can think about this then as something that looks like this, and you have your hydrogen over here that you transferred from the other side. I'm just going to mark it here with orange so it's clear that where this hydrogen comes from. Another one that you actually have seen before is the reverse reaction, where we essentially dealing with a fragmentation. And this is something that we have seen in the decarboxylation as part of the aldol chemistry that we have looked at. And if you remember, there were some reactions where we said that we can easily remove this carboxylic acid group from the system. And that's exactly the same way, just now that, that we have a system that is a little bit more, more involved, a little bit more laden with heteroatoms. But the way we have looked at this before is that we said like, well, you have the electrons from this system that can push in here and grab the proton. You have the electrons in this bond that can go down here to form a new CO double bond. And you have the electrons in this CC bond that can go in here to form the double bond of the enol. And if you go through this reaction, if you remember, what you got out was first the enol. And as a side product, you essentially generated CO2 that kind of escaped the reaction mixture, right? And after that, you know, obviously, this can tautomerize to then form the ketone, right? So if you don't remember that, that's something you might want to go back in your notes and look at that again. So that's basically a decarboxylation. And it also falls under these group transfer reactions. Now, the last one that we have seen before already, we kind of hinted at that a little bit, is the group transfer reactions that we saw as part of the reduction of double bonds. And this is basically the reaction of diimide with alkynes or olefins. So reduction of double bonds. And we had one example as part of our lecture when we were talking about reducing double bonds, where we had diimide. So diimide. And we reacted this, I don't remember what it was exactly, but maybe it was a triple bond or a double bond. It's exactly the same. Let's pick a double bond here. And what we're going to do is we're going to transfer these two hydrogen atoms in one step, essentially, to this double bond. So you can think about this a little bit as taking the electrons out of this bond, pushing them over here, taking electrons out of this pi bond, pushing them over here, and these back into the nitrogen-nitrogen bond. And this again is a 6 pi electron process. And it gives you basically the transfer of two hydrogen atoms to the same side of this triple bond. So on one side now in the products, you have nitrogen, which is essentially the driving force for this. And then and here you have remaining a double bond and 2 hydrogens that you transferred from this diimine. Right? So this is also a classical group transfer reaction, and it accomplishes the same product as you get from Lindlar catalysis. So same product as Lindlar catalyst. So the poison catalyst that gave you like a partial reduction of a triple bond. Now the same thing works also with single simple olefins. So if you have something like this, again a diimine, and you react this with an olefin, you get the same product. So let's do hydrogen, hydrogen. You basically get dinitrogen again, and as a side product, or as the product is essentially the reduction product, in this case, hexane. So I have hydrogen, hydrogen, and then you have the 2 hydrogens that got transferred from here. All right, so these are basically just the last group, the group transfer reactions that we wanted to introduce today. I know that this was kind of like a stampede through this field of pericyclic reactions, but I think it's important that you see like the diversity first before at the beginning of next class, we're going to start diving into much more detail into the cycler addition reactions, and specifically how these Diels-Alder reactions essentially work in detail on an orbital molecular basis. That's what we're going to cover next time, and then we're going to work slowly our way through the chelotropic reactions, through the electrocyclizations and the sigmatropic rearrangements. And we're going to cover a little bit of this group transfer at the end again, but this is going to be only a minor part of this chapter. So I'll see you all on Thursday. And just as a reminder, I have office hours today again at 9:30. And I will upload this lecture as soon as it has rendered on my computer. Okay? So see you next Thursday.